Welcome to the lecture series on CFD Part 2. This is lecture 27 on solution methods for overlapping grids. This lecture starts with an introduction to overlapping grids, their advantages and disadvantages compared to alternative approaches for the simulation of complex flows. The greatest advantage is the possibility to simulate flows around moving bodies with arbitrary paths, including body contact. The main challenge is the automation of the activation and deactivation of overlapping control volumes from two or more grids. Two kinds of coupling of overlapping grids are then described in detail: explicit coupling via boundaries and implicit coupling via iteration matrix. The requirements for accuracy and robustness of solution methods for overlapping grids are described next. Finally, Simcenter STAR-CCM Plus software is used to highlight the features of solution methods for overlapping grids on three examples. In one, automation of parametric studies like different angles of attack in simulation of flow around bodies is shown. The other example is the mixer studied in lecture 26 using a sliding grid interface. Here, the two approaches are compared. Finally, in the third example, a mixer with two impellers is used to highlight the ability of overlapping grids to handle moving parts with intersecting paths where the sliding grid approach is not possible. Overlapping grids in different flavors have been used by many researchers since the early days of CFD. More recently, they became available as an option in commercial and public CFD software, where they are usually used for three reasons: to achieve high grid quality near bodies when using block-structured grids, to simplify parametric studies of flows around bodies at different relative positions, and to simulate flows around moving bodies, especially with crossing paths. Methods of this kind are often associated in literature with names like chimera grids. The chimera is a mythological creature with a lion's head, goat's body, and snake's tail. Offset grids or composite grids. Usually, one creates a background grid disregarding moving bodies, which is only fitted to external boundaries like inlet, outlet, symmetry, or far-field boundaries, where appropriate boundary conditions are prescribed. One or more overlapping grids attached to moving bodies, which partly or fully overlap with the background grid, are created separately. They include the boundary conditions at body walls, while outer boundary is used only for the coupling with the background grid. Grids attached to bodies usually cover only the volume up to a certain distance from the body, or within a simple shape containing the body. If bodies are moving, the grids attached to them are moving too, usually as rigid bodies, but they may also deform as they move. See lecture 26 for details related to moving and deforming grids. Block-structured grids, in which some blocks have conformal and some overlapping interfaces, are widely used in proprietary codes within the defense industry. There are also public codes using this approach. See NASA Chimera Grid Tools Users Manual version 2.2 from 2018. There is a special symposium on overlapping grids that takes place every 2 years since 1992. See the official website www.offsetgridssymposium.org for more information. Overlapping grids have several advantages over alternative approaches. Here are the main ones. One can better optimize the grid quality near a wall in a complex geometry than in a single grid. This is especially the case when block-structured grids are used. There are many CFD codes that use block-structured grids, and allowing blocks to overlap greatly extend the usability of such codes. The grid quality near a wall is preserved if the body moves, because the grid moves with it and does not have to deform as would be the case otherwise. Deteriorating grid quality due to its deformation as a consequence of body motion can seriously affect both the accuracy of solution and the robustness of the solution method. Parametric studies with bodies at different angles of attack or different relative positions can easily be realized with overlapping grids without changing the grids or boundary conditions. One simply repositions the overlapping grids and continues the computation. One such example is presented in slides 16 to 20. With overlapping grids, arbitrary body motion can be accounted for, which otherwise may not be possible with other methods, or not at the same level of accuracy. This includes motion of multiple bodies with crossing paths and even contact of bodies. Immersed boundary methods are usually the only alternative for such simulations, but they have disadvantages with respect to accuracy when boundary layer effects are dominant. However, nothing comes for free. Overlapping grids also pose some challenges on the way to realize all those advantages. Users of commercial software are less effective than those who want to implement this capability into their own CFD code. Firstly, one needs to devise a suitable way of coupling the solutions on different grids. There are many possibilities, differing in the implementation effort, applicability range, robustness, and accuracy. Secondly, one needs to identify control volumes or grid points in the overlapping zone which are to be deactivated. This is often called hole cutting. If grids are moving, this must be done in each time step. It is therefore important that this operation itself is efficient and not imposing too strong constraints on parallelization of the code. When grids are moving, domain decomposition for parallel computing may need to be redone frequently. This requires redistribution of cells or grid nodes between processors and reduces the efficiency of parallel computing. See Lecture 25 for details on parallel computing in CFD. When small gaps between bodies exist, or a contact or separation of bodies is to be accounted for, overlapping grids need to undergo special adaptation. This may include modification of solver and boundary conditions. Let us now see how the solutions on overlapping grids can be coupled. Part of the background grid, which is covered by the body and the overlapping grid, is deactivated, except for a narrow overlap zone where both grids are active. Discretization and solution methods used for all grids are usually one of those described in this lecture series. Only the coupling of solutions on individual grids is specific to overlapping grids. One possibility is to treat the outer surface of the overlapping grid and the surface of the hole created by deactivating some cells in the background grid as boundaries. On the part of such overlapping boundary, where the flow enters the solution domain of a particular grid, inlet or Dirichlet conditions are prescribed. Variable values needed at an inlet boundary are obtained by interpolation from active cells or grid nodes in the other grid. On the part of the overlapping boundary where the flow leaves the solution domain, pressure is specified. Required pressure values at boundary nodes are obtained by interpolation from active cells or grid nodes in the other grid. The problem with the method described in the preceding slide and with similar methods based on coupling via boundary conditions is that convergence of the iterative solution procedure is not guaranteed. Convergence problems are usually encountered when the flow over a larger part of the overlapping boundary is parallel to it, so that inlet and pressure conditions keep swapping. The method is explained below on the example of flow in a channel with a semi-cylindrical obstacle. The background grid in the rectangular channel is Cartesian, while the grid around the obstacle is polar cylindrical. Both grids are optimal for the respective geometry. Because the obstacle is not moving, the hole in the background grid, that is, removing inactive cells, can be done a priori as part of pre-processing. In this case, a simple block covering the obstacle is removed. See next slide. Only half of the channel is considered with symmetry boundary conditions in the midplane. This is done to enforce a steady-state solution without vortex shedding. The flow is turbulent at Reynolds number equal 1 million based on the mean velocity and channel width. It is simulated using the K-epsilon turbulence model. See lectures 32a and 32b for information about turbulence modeling for Reynolds average Navier-Stokes equations. This figure shows schematically the solution domain and the boundary conditions on each grid. Note that the selection over which part of the overlapping boundaries inlet and pressure conditions are applied has been made in advance. This is possible in this case because the extent of separation zone can be estimated. Fixing the boundary conditions avoids the possible convergence problems outlined in preceding slide. The results from computation using overlapping grids are compared with results obtained using a block-structured grid with conformal interfaces. These two plots show the respective grids. Note that it is trivial to generate the background and the overlapping grid on the left, while it is more complicated to create a good quality block structured grid shown in this plot. The plots below grids show the isobars computed on the respective grids. The results are very similar, although not identical. The maximum pressure at the front stagnation point is slightly higher on the block structured grid, while the minimum pressure on top of obstacle is practically the same. Pressure contours in the overlapping zone from both grids fall on top of each other, except in the obstacle wake, where a small offset is visible. These two plots show velocity vectors in the immediate wake of the obstacle, from overlapping grids and from block-structured grid. One cannot see any significant difference in the position of separation line or the length of recirculation zone. These two plots show residual histories for mass and momentum against outer iterations. The convergence rate is somewhat slower with overlapping grids than on block-structured grid when explicit coupling is used. Variable values at overlapping boundaries are updated after each outer iteration. Convergence rate would probably be somewhat faster if the update of boundary values was performed after each inner iteration within the solver of linear algebraic equations. However, this would require significant programming effort. Here, one complete outer iteration of the simple algorithm is performed on each grid in a sequence until convergence criterion is satisfied. Residuals were reduced 10 orders of magnitude and no convergence problems were encountered. Another option is to build the coupling of grids into the matrix A of the linear equation system for each equation solved. In this way, the continuity and momentum equations are solved simultaneously on all grids. That is, the grids are coupled at the inner iteration level. The implicit coupling of grids is highlighted with the help of this figure, which shows active cells on two grids which overlap. Blue lines denote the background grid, while red lines are from the overlapping grid attached to one body. Acceptor, also known as ghost or hanging nodes, and A for the red grid are defined such that discretization at cell P can be performed as if neighbor cells were also active. Variable values at acceptor cells are obtained by interpolation from a selected set of donor cells from the other blue grid. For example, the discretized equation for the red cell labeled P refers to an acceptor neighbor NA, marked by an open circle, via fluxes through the phase between P and NA. The variable value at the center of acceptor cell is replaced by an interpolation expression involving donor cells from the blue grid, here N4, N5, and N6, given by this expression. Here, alpha 4, alpha 5, and alpha 6 are interpolation factors that add up to unity, obtained by fitting linear shape function to the three nearest neighbors of NA from the blue grid, N4, N5, and N6. In the algebraic equation for the red cell P, there will be 6 off-diagonal coefficients in the linear equation matrix. 3 neighbors are from the same grid, N1, N2, and N3, and 3 neighbors come from the overlapping grid, N4, N5, and N6, via NA. There are many different options for interpolation between donor cells and for the number of donor cells to be used. In addition to the linear shape function outlined in the preceding slide, one can also use only the variable value and the gradient from the nearest neighbor of NA. Here it would be N5, as given by this expression. Phi NA is equal phi N5 plus gradient of phi at N5 times vector distance from N5 to NA. Higher order interpolation functions can also be used. There are many possibilities to choose from. To ensure that interpolation errors at acceptor nodes are of the same order as interpolation errors for computing cell phase variable values for convection fluxes, the cell size in the overlapping zone should be similar in both grids. If two grids are to be coupled in a narrow gap between two walls, At least 4 cells across the gap should exist in each grid. Adaptive grid refinement is desired when grids are moving so that different grid zones overlap in narrow gaps. See lecture 33 for details on adaptive grid refinement. This is especially important if body contact is to be simulated. One should use adaptive grid refinement until the distance between bodies becomes smaller than a tolerance at which the contact is declared. Contact modeling decides how the bodies move after the contact has taken place. Let us now see how overlapping grids work in practical applications. Assume we need to compute forces on a body at different angles of attack. Here, a model of a vehicle is used to demonstrate the approach to parametric studies. The left figure shows a horizontal section through the grids around the car model at 30 degrees angle of attack. The figure on the right shows a cross-section through the solution domain as indicated by this green line. The flow is from left to right. To enable efficient and automated conduction of such parametric studies, we create a background grid for the environment and define boundary conditions on it. The background grid is in this case Cartesian, with one level of refinement around the body and in its way, as shown in this plot with blue lines. The solution domain is much larger than shown in these plots. The overlapping grid attached to vehicle is polyhedral. It has prism layers on vehicle walls and is locally refined near walls and in the wake. This grid can be rotated around a vertical axis at vehicle center to change the angle of attack. Thus, there is no need to regenerate the grids or change boundary conditions when performing computations at different angles of attack. In Simcenter STAR-CCM Plus software, the process of sweeping the desired range of angles of attack can be automated. These figures show pressure distribution on the vehicle and floor for 6 different angles of attack: minus 30 degrees, minus 15 degrees, 0 degrees, 15 degrees, 30 degrees, and 45 degrees. We see increased pressure at stagnation points where the flow is slowed down and low pressure near edges where the flow is accelerated. These figures show velocity vectors around the vehicle in a horizontal section plane for 6 different angles of attack, corresponding to those for which the pressure distribution was shown in the preceding slide. The flow is turbulent, and the Reynolds average Navier-Stokes equations are solved together with the K-epsilon turbulence model. See lectures 32a and 32b for a description of turbulence models and boundary conditions. The solution domain is much larger than the zone shown. This diagram shows the forces on vehicle in flow direction: black line, cross flow direction, blue line, and vertical direction, red line, for 8 angles of attack. When forces for one angle of attack converge, the vehicle is, with its grid, rotated to another position and the computation continues until the prescribed range is finished. This simulation is performed only for demonstration purposes with a simplified vehicle model. Let us now turn back to the mixer model from lecture 26. The geometry is shown in this picture. For dimensions, boundary conditions, and solutions obtained with sliding grids, see slides 25 to 30 of lecture 26. The overlapping grid attached to the impeller is the same as the moving region in the sliding grid approach from lecture 26. It is shown here in red. The background grid is generated for the vessel geometry without impeller, shown here in blue. This plot shows a horizontal section through both grids before the computation was started. The plot on the right shows the same section during simulation. The central part of the background grid has been deactivated and the two grids overlap in a narrow zone. The results from a simulation using overlapping grids will be compared with results obtained in lecture 26 using sliding grids. This slide shows the pressure field on the left and flow pattern on the right in one horizontal section through the mixer. The impeller rotates counterclockwise, and we see high pressure ahead of blades and low pressure on the rear side, as expected. The flow pattern shown in this plot indicates recirculation behind baffles on the outer vessel wall. This slide shows the pressure field on the left and flow pattern on the right in one vertical section through the mixer. The impeller rotates counterclockwise, and we see again high pressure ahead of the blade and low pressure on the rear side. The flow pattern shows that blades are pushing the fluid forward and downward and sucking it from behind and above. This leads to a recirculation pattern visible in this plot, which enhances the mixing process. In these two plots, pressure distribution in a horizontal section plane computed using overlapping grids in the upper plot and sliding grids in the lower plot are compared. Around impeller, pressure contours are practically the same in both plots. In the outer zone, contours are the same in each quarter in the simulation using sliding grids, but there are small differences between left and right-hand side in the case of overlapping grids. This diagram shows the comparison of thrust, that is, force in the direction of rotation axis, generated by the impeller from simulations using sliding and overlapping or offset grids. Grids were generated automatically by Simcenter STAR-CCM plus software using the same setup in both cases. See slide 21 from this presentation and slide 26 from lecture 26 for a direct comparison. Considering that the difference between highs 0.0098 and lows 0.0088 is relatively small compared to the mean value 0.0093, and that the grids are relatively coarse, the difference between the solutions is negligible, around 1%. This slide shows a comparison of torque exerted on fixed mixer blades on the left and impeller blades on the right from simulations using sliding from lecture 26 and overlapping or offset grids from this lecture. Differences in solutions from the two approaches are not large, on the order of circa 1%. They would be smaller on finer grids. In cases where sliding grids can be used, there is no advantage in using overlapping grids. However, when paths of moving parts are crossing each other, sliding grids cannot be used, but overlapping grids are applicable. One such case is presented in the following slides. This slide shows a horizontal section through overlapping grids in a mixing vessel with two counter-rotating impellers. Both impellers are the same as the impeller from the preceding test case. Because of intersecting paths of impeller blades, sliding grids cannot be used in this case. The left figure shows a section through all grids prior to the start of simulation. The background grid, black lines, is generated for the empty vessel without impellers. For each impeller, a polyhedral grid with prism layers and local refinement at walls is generated. Red grid for the left impeller and blue grid for the right impeller. The right figure shows a section through the active cells of the three grids in one time step during simulation. In the zone where three grids overlap, the priority is given to the blue grid, but it would be equally appropriate to favor the red grid. This slide shows animations of velocity fields in the axial section through the mixer on the left and in cross section through impeller blades on the right, computed using overlapping grids. The fluid and rotation speed of impellers are the same as in the mixer with a single impeller. In the horizontal section, the fluid follows the motion of impellers, with highest velocities between the two impellers. In the vertical section, we see multiple vortexes, some of which are relatively steady, while the others are moving around, driven by impeller rotation. Plotted are velocity vector projections into the section planes. Small tangential vector components, like here, does not necessarily mean stagnant fluid. The velocity component normal to the section plane may be significant. These plots show pressure fields in the axial section through the mixer on the left and in a cross section through impeller blades on the right, computed using overlapping grids. Pressure is high on the front part of each blade and low on the rear part, except for this blade, because its front part faces the rear part of this blade of the other impeller. In these contours, we cannot see where the grids overlap. These plots show the variation of thrust, the left figure, and torque, the right figure, on blades of the left impeller from the simulation using overlapping grids. Both quantities vary in a wider range and have lower mean values than in the case of a mixer with a single impeller. See slides 29 and 30 in lecture 26 for a direct comparison. Let us briefly discuss the main challenges associated with overlapping grids for programmers of CFD codes. When more than two grids are involved, such as in the last example, selecting which cells to deactivate, how to shape the overlap zones, and which grids to couple is not trivial. There are no equations or other solid rules to follow. Programmers must select one of the many options, which is usually justified by trials from numerical experiments. For example, one could insist that all overlapping grids are coupled only with the background grid, and that overlapping grids do not overlap each other, as was the case in the last example. One could also maximize the red grid region rather than the blue, or deactivated all cells in overlapping grids which are further from walls than a prescribed distance. Another tricky thing is the integration of a volume, for example, to determine the amount of one species. Because active cells overlap, the volume of all active cells is larger than the volume of the solution domain. Here is a summary of this lecture. Overlapping grids have several attractive features, but also pose some challenges in implementation. Fortunately, there are software tools in which most of good choices have been implemented. See the list in the next slide. With overlapping grids, one can easily perform studies of flow around bodies at different relative positions, for example, different angle of attack, by repositioning the overlapping grid on a fixed background grid. One can also perform simulations of flow around moving bodies with crossing paths, which is otherwise only possible using immersed boundary methods. Grid quality, especially near bodies when boundary layer effects are important, can be optimized and preserved during body motion. The challenges are related to the automation of activation and deactivation of cells covered by overlapping grids, domain decomposition for parallel processing, and computational volume integrals over the whole solution domain.